This is a lesson on sections 5.2 and 5.3 for Math 128 at the University of Dayton. This involves using matrices to solve systems of equations. This is an example of a system of equations. You can see that there are three equations and three variables, x, y, and z. They don't have to be called x, y, and z. They could be other letters, or they could be letters with subscripts so that you can have as many as you want. For example, the first column could be x sub 1, the next column could be x sub 2, and the third column with coefficients 6, 5, and 2 could be x sub 3. The fourth column after the equal sign are the constants. They don't have any variables associated with them. The key to understanding this is that the variable's purpose in terms of solving the system of equations is to just keep the right coefficients lined up. So if I just dropped the variables and wrote only the coefficients, we would have what's called a matrix, an array of numbers. So this is just the coefficient matrix, 2, 4, 6, 3, 8, 5, negative 1, 1, and 2, that are the coefficients of x, y, and z respectively, and the constants 22, 27, and 2, that column on the right. As I mentioned, those first set of 3 by 3 of a 3 by 3 matrix, 3 columns and 3 rows, is called the coefficient matrix. The whole thing together with the line separating the coefficient matrix from the column matrix of constants is called an augmented matrix. Augmented means you've added something to it. So we've taken the coefficient matrix and augmented it with the column of constants. And that's all we need to work with as long as we keep all the columns to them with themselves. The row-reduced form of a matrix is what we're aiming for. Each row, consisting entirely of zeros, lies below all other rows. In fact, you can pause this and read these for yourself, but let me show you what a row-reduced form of a matrix looks like. It would look something like this. Every row, and row, you know, means left and right, so let me get my pointer right here. So this right here is an example of row. That's row 1, and below it is row 2, and below that is row 3. Every row is led by a 1, okay? Or it could be all zeros. And above and below each leading one are only zeros. So this first one up here in the upper left-hand corner, let me find my marker. There it is, way over there. This first one right here has only zeros below it. This second one right here has a 0 above and below it. This third one right here has zeros above it. And then the fourth column are the constants. Row-reduced echelon form has leading ones in every row, and furthermore, every lower row, the leading one is to the right of every row above it. So the furthest to the right is this third one, okay? The furthest to the left, and we'll always start with that in the upper left-hand corner, is a 1 right here. If we can get it in row-reduced echelon form, we've solved the system, because if you remember, this row right here represented the x's, this represented the y's, and this represented the z's. So if we rewrote this, it would be 1x plus 0y plus 0z equals 3. In other words, x equals 3. In similar fashion, this means y equals 1 and z equals 2. Okay? So that's why we want to put things in reduced row echelon form. How we do that is what this lesson's all about. So let's suppose we had a system of equations, for example, 2x plus 4y plus 6z equals 22, 3x plus 8y plus 5z equals 27, negative 1x plus y plus 2z equals positive 2, and we want to put it in reduced row echelon form. In order to do that, we use what are called row operations. The row operations are the same operations as what you can use if you actually had the equations. You could interchange any two rows. For example, put the middle row on top and the top row in the middle. It just is like rewriting the equations in a different order. You can replace any row by a non-zero constant multiple of itself. So if I wanted to multiply the bottom row by 2, I could turn the bottom row into negative 2, 2, 4, and 4. That's like multiplying both sides of an equation by a number, which you know you can do. But be careful. Remember that it has to be a non-zero constant, otherwise you completely wipe out the equation and get 0 equals 0, which is useless. Finally, you can replace any row by the sum of that row and a constant multiple of any other row. In other words, we can add equations, which is what we've always been doing, except now we're going to do it with rows of the matrix. So let's see how we can use that to take our matrix and put it in reduced row echelon form. So if we started with that very same matrix, we have some options here. Okay, the options are, first of all, we want to put a 1 right here. Here's one option. Multiply the entire top row by 1/2. Half times 2 is 1, half times 4 is 2, half times 6 is 3, half times 22 is 11. That's probably the easiest way. And in fact, your book does this exact problem, and they do it that way. But there are other options as well. We could also take row 2 minus row 1 and replace row 1 with that. For example, 3 minus 2 is 1. And then 8 minus 4 is 4, 5 minus 6 is -1, and 27 minus 22 is 5. But I think what I'm going to do is I'm going to take row 3 and add it to row 1, and then replace row 1 with that combination. So I'm going to take row 1 plus row 3 and replace row 1. The notation is we always replace whatever we wrote down first, but just to be careful so that you all understand, I'm replacing row 1, and I'm doing nothing with the other 2 rows other than maybe using them. So in this case, row 3 stays as it was because I'm only replacing row 1. So I'll just write it 1, 1, 2, and 2 with a little vertical line there. Row 2 stays the same, 3, 8, 5, and 27. And then I said I was going to take row 1 plus row 3. Well, 2 plus -1 is 1. Bingo, there it is. 4 plus 1 is 5. 6 plus 2 is 8. 22 plus 2 is 24. Okay? Now that we have that 1 there, we need to have zeros below it. So we take care of its column by placing zeros where we need to. And we use row 1, because of that 1 in the front of it, to do that. So for example, if I take row 2 minus 3 times row 1, 3 times 1 is -3. 3 minus 3 is 0. We will get a 0 in row 2. And if I take row 3 plus row 1, and replace row 3 with it, 1 plus -1 is 0. So our next matrix is, the top row hasn't changed. We've used the top row, but we're not changing the top row. So that stays as is. But 3 minus 3 times row 1, 3 minus 3 times 1 is 3 minus 3 is 0. That's what we want. 8 minus 3 times 5 is 8 minus 15. Little math there will show you that that's -7. 5 minus 3 times 8 is 5 minus 24. 5 minus 24 is -19. Okay? 27 minus 3 times 24, that's 27 minus 72. Let's see, 27 minus 72. That's the opposite of 72 minus 27. So 12 minus 7 is 5. 6 minus 2, 45. So it's -45. Okay. That's a tough one, isn't it? Let's do the same thing with row 3. Row 3 plus row 1 is what the instruction says. And remember, it's going to replace the first one listed, row 3. So I just add them. 1 plus -1 is 0. There it is. That's what we want. 5 plus 1 is 6. These are easier numbers. 8 plus 2 is 10. Okay. And 24 plus 2 is 26. Okay. And so we have that. Now, what do I do next? Well, I want to put a 1 where this -7 is. This is called our pivot element. But we're going to do it a little bit differently than how the book describes it, but I want you to look at how the book does it. So what's our next operation going to be? Well, one thing I could do is divide the entire row by -7, but then we'd end up with some unfortunate fractions like -19 over -7 and -45 over -7. So instead, I'm going to take a little intermediate step and multiply it by -1. Okay, so I'll just write negative row 2 to get some positives there, and you'll see why in a moment. I'm looking ahead. So the top row stays the same, 1, 5, 8, and 24. Multiply this by -1, 0, +7, +19, +45. You don't always have to deal with that like that. Sometimes we can use negatives, but in this case you'll see why in just a moment. Bottom row stays the same, 0, 6, 10, and 26. Does anyone out there see why I did that? Well, it's because now I have a +7 and a +6, and I've subtract them, I get a 1, and that's what I want, is I want to have a 1 right here. So I'm just going to take row 2 minus row 3 and replace row 2. So it means row 3 doesn't change, 0, 6, 10, 26. But row 2 gets replaced by row 2 minus row 3. Here's the advantage. 0 minus 0 is still 0. Notice we still have 2 zeros in the first column. 7 minus 6 is 1. That's what we wanted. 19 minus 10 is 9. 45 minus 26 is 19. And then the top row stays the same. 1, 5, 8, and 24. So now what do we need to do? Well, this 5 needs to be converted to a 0, and the 6 needs to be converted to a 0, because you remember leading ones have only zeros above and below them. So in order to do that, we can use that 1, because you can multiply 1 by anything to get whatever you want. So let's take, and let me show you what I mean. If I take row 1 minus 5 times row 2 and replace row 1, 5 minus 1 times 5 is 5 minus 5. That'll put a 0 there. If I take row 3 minus 6 times row 2 and replace row 3 with it, 6 minus 6 times 1 is 6 minus 6. That'll put a 0 there. So let me continue here. I'm not changing row 2. I'm using row 2. So 0, 1, 9, 19. Close my bracket there. Okay, row 1 minus 5 times row 2. 1 minus 5 times 0 is still 1. Notice that doesn't change. 5 minus 5 times 1 is 5 minus 5 is 0. Good. 8 minus 5 times 9 is 8 minus 45. 5 times 9 is 45, which is negative 37. And 24 minus 5 times 19 I think I'll use a calculator for this one. Let's see. 24 minus 5 times 19. I get negative 71. Okay. Okay. So this is negative 71. Looking pretty weird, isn't it? Okay. That makes sense. It's 24 minus 95. Okay, let's do this operation. Row 3 minus 6 times row 2. And remember, we're going to replace row 3. So we take 0 minus 6 times 0 is still 0. 6 minus 6 times 1 is 6 minus 6. It's 0. Ta-da! 10 minus 6 times 9 is 10 minus 6 times 9. 10 minus 54 is negative 44. And then 26 minus 6 times 19. 26 minus 6 times 19. Once again, I'm going to use the old calculator on that one. 26 minus 6 times 19 is negative 88. Okay? And look what we have. We have a 1 here, here. We have zeros here, here, and here. We need to put a 1 here. Can you see the really obvious way to do that? Well, since that's a 44 and that's an 88, how about we just divide by 44? Watch this. Just take row 3 divided by negative 44, or negative 1/44 times row 3. Nothing else has changed. So row 1 stays 1, that's a 1, 0, negative 37, negative 71, vertical line here, close the bracket here. Row 2 stays the same, 0, 1, 9, and 19. Row 3, I divide by negative 44, multiply by 1 over negative 44. So I get 0, 0, anything times 0 is 0. That's the great thing about having all those zeros. Negative 44 divided by negative 44 is 1. Negative 88 divided by negative 44 is 2. And I think you can already see that we have one of our results. Z is 2. The X column, the Y column, and the Z column. So Z is equal to 2. I need to now put zeros above this 1, but that's easy. If I multiply this by negative 9 and add it to 9, I get 0. So 9 minus 9 times 1, row 3 minus 9 times, row 2 minus 9 times row 3. So that's our next operation. Row 2 minus 9 times row 3. And for row 1, we'll do it at the same time. It'll be row 1 plus 37 times row 3, because negative 37 plus 37 is 0. Okay? So row 1 plus 37 times row 3. Okay? Which means I'm changing row 2 and row 1. Row 3 stays the same, which we want it to do because it looks perfect. So let's see what we get. 0 minus, let's see, we're doing row 2 minus 9 times row 3. So I'm changing row 2. Row 2 is here. 0 minus 9 times 0 is still 0. 1 minus 9 times 0 is still 1. 9 minus 9 times 1 is 9 minus 9, which is 0. 19 minus 9 times 2 is 19 minus 18, which is 1. Cool! We know that y is equal to 1. Let's keep going. Row 1 plus 37 times row 3. That's right here, is going to replace row 1. So we have 1 plus 37 times 0 is 0. 0 plus 37 times 0 is 0. Negative 37 plus 37 times 1 is negative 37 plus 37 is 0. I don't know why I wrote a 0 over there. It's clearly a 1. Let me change to an eraser here. At least I caught my own mistake this time instead of waiting for you to do it. That's a 1. Okay. And remember, we're still doing row 1 plus 37 times row 3. So this is negative 71 plus 37 times 2. That's negative 71 plus 74. Folks, that's 3. So our final answer is that x equals 3, y equals 1, z equals 2. Or if you want to write it like an ordered triple, that's 3 numbers in an ordered pair, sort of. You'd write it as 3, 1, 2. And that's one way of putting in reduced row echelon form. You try to put 1s in the column as much as possible by whatever means necessary. And like I said, we could have started differently. We could have started by just dividing the top row by 2. In fact, I think that's how your book authors do that. So if you look at the section 5.2 example 2, you'll see this exact same problem done a little bit differently, and I think a little bit more efficiently, because that's what I would have done too, but I wanted to show you something different. So that's what we do. We get zeros, we get ones along a diagonal and zeros everywhere else. Ideally, the ones will be on a nice diagonal, but sometimes they stair step, which is what echelon means. Okay? These are some examples of augmented matrices that are in reduced row echelon form. You can see the first one is exactly like the last one, meaning that the coefficient matrix just has a diagonal of ones with zeros every place else, and then the column to the right is whatever it ends up being. But the second one is in reduced row echelon form also, because the only ones we have are leading ones, and they make that stair step, and the bottom row is all zeros, just like it needs to be. All zero rows are at the bottom. And the third one, surprisingly, is also in reduced row echelon form, because we have a 1 here. We jump over to here for our next leading one, but it is to the right. It might be 2 columns to the right, but it's to the right. And our third one is also to the right. So these are all in reduced row echelon form. These, on the other hand, are not. The first one's obvious. We don't have the stair-step formula, but if we just switch these two rows, then that would put this one up here and put this one down here, and everything would be okay. So we're one step away from having a reduced row echelon form. This one's not in reduced row echelon form because here we have a leading 2, and also we don't have a 0 below this 1. So if we multiplied this middle row by -2 and added it to the third row, that would put a 0 here, and then do whatever is necessary to put a 1 here. Okay? But this is not in reduced row echelon form because we don't have all leading ones, and because this one does not have a 0 below it. This, of course, is not in reduced row echelon form because this is not a leading 1, although we do have the stair-step pattern. So you have to be careful. Sometimes they're not in reduced row echelon form, sometimes they are, and you have to fix them if you can. This one has 3 variables, x, y, and z, or x1, x2, and x3, representing the first three columns. But it only has 2 equations that are useful. The bottom equation is all zeros, which is okay, but it means that we're going to have a different kind of solution. The leading ones in reduced row echelon form are called pivot elements, and they're in what are called pivot columns. And they represent what are called pivot variables. So x and y are pivot variables because they both have leading ones associated with them. The other columns are called free columns, and they represent free variables. So z is an example of a free variable. So these are pivot variables, and this happens to be a free variable in this case. Okay? And they can take on any value. They're free. What we end up with, if we write them as equations, is this first equation, because 1x minus 1z equals 0, which is this, and it translates into x equals z. The second row, can you tell what that is? Maybe write it down yourself if you want to pause. But it's y minus z equals -1, or if we solve for y equals -1 plus z. You write the equations and then solve for the pivot variables in terms of the free variables. Now, what this leads to is what's called a parameterization. So starting from the right, meaning in this case z, you allow the free variables to equal some parameter and evaluate the pivot variables. Or if you write the equations and solve for the pivot variables, anything on the right side of the equation becomes a parameter. So if, for example, we let z equal the parameter t, then x becomes t and y becomes -1 minus t. Or, as an ordered triple, x is t, y is -1 plus t. Yes, I know I should have said plus t, not minus t. Right there, that's a plus sign. And z is also t. What that means is we have an infinite number of possible solutions by letting t equal anything. So for example, if t equals 0, we get 0, -1 plus 0, and 0, and that will be a solution to the original equations that we had up here. For example, this first row represents the equation x plus 2y minus 3z equals negative 2. Okay? Well, if x is 0, y is negative 1, and z is 0, this becomes 0 plus 2 times negative 1 minus 3 times 0 equals negative 2. And sure enough, that's true. But it'll work for any other value of t. If I let t equal 4, then we have the point 4, negative 1 plus 4 is 3, and then 4. That'll also work in any of these equations. Just using the top equation, it becomes 4 plus 2 times 3 minus 3 times 4. Okay? 4 plus 2 times 3 minus 3 times 4 is 4 plus 6 minus 12. 10 minus 12 is negative 2, and guess what? It says it's supposed to equal negative 2. So we have an infinite number of answers because you have an infinite number of values you could put in for t, including fractions and irrational numbers. Okay? So that's the parametric solution to that system of equations. It has an infinite number of solutions. All zeros at the bottom is fine. On the other hand, if you end up with all zeros on the left of the line, but a non-zero on the right, you have a problem. Because what you end up with is 0 equals 1. This row right here would represent 0 x's plus 0 y's plus 0 z's equals negative 1. So that should be negative. And that says 0 equals negative 1, and that is just plain wrong. If you see something like that, that means your original system of equations of, in this case, x plus y plus z equals 1 for this row, 3x minus y minus z equals 4 for this row, and x plus 5y plus 5z equals negative 1 for this row, is inconsistent. There is no solution. Okay? So 0 equals not 0 is always wrong and means no solution. And that is the end of the lesson. You're welcome to go back and pause it wherever you need to, but that's the basis of what was taught on the Tuesday before Thanksgiving. So I'll see you all in class. Have a good day, and happy Thanksgiving.